name is Dr. Anna Scott. I'm the president and co-founder at Project Canary. For those who aren't familiar with Project Canary, we are primarily a Colorado-based public benefit corporation. What that means is that we're legally incorporated in a way that holds us accountable to the double bottom line of both profit and social good. My own background is not in the methane space. I come to this from the world of applied math and then a PhD in atmospheric science, where I looked at temperature in urban areas and looked and set up networks of sensors in cities and rural areas around the world. And it really got me interested in this idea about air quality. And so I started tinkering with sensors when I was in graduate school. My poor PhD advisor was like, man, cut that out, you're never gonna graduate. I did eventually started a company that got rolled up and wrapped into Project Canary this fall. And what we do at Project Canary, I think, really has one kind of theme. I don't really want to keep this conversation too Project Canary specific today, but certainly this is like the paradigm I bring into this. At Project Canary, what we do is we provide trusted, independent data, and we think about this in two sort of different flavors. One of which is through our certification programs where we go through and verify that natural gas has been produced in the, has achieved the highest standards of production with respect to 4 areas: air, water, land, and community. And it's so great to see customers like EQT here on the line. And then we also do continuous monitoring, which in many cases is paired together with our certification program, where we use high fidelity IoT devices to measure methane and calculate carbon footprints. But what I wanted to talk to everyone today about is this idea of continuous monitoring, why I think it's important, and how I come to it. Fundamentally, I think this is a conversation that is technology agnostic. I got dragged into building the silly sensors because they were, what we heard was that there wasn't a good solution on the market. That being said, Project Canary is, and I think will shortly publicly announce that, but I take this as a public announcement, that we're going technology agnostic. So we're going to be welcoming additional sensors onto our platform. Again, I think this is a space where when we all work together, we all win. I am so excited to be joined by, so many awesome startups on this call that have really paved the way for us to be able to do what we do. So thank you everyone for your hard work. For those folks who haven't heard this a million gazillion times, I think for me, this was really how I got started in this space. This is Alvarez et al. in 2018, which highlighted the issue of leakages from the US oil and gas supply chain, showing that EPA inventory estimates were overestimated perhaps by up to 60%. And the reason why that could be a problem is that methane has a radiative forcing that's anywhere from 25 or so to 86 times worse than carbon dioxide, depending on the time scale that you look at. And so this means that methane emissions in the upstream oil, natural gas sector are a big climate problem. Now, a lot of these, or a significant portion of these emissions, come from sources that are just it's a hard problem. It's a hard problem to fix. So, for example, here I'm showing well data and pipeline data for just for the U.S. And if you look at the Permian Basin, what you can note is that there's not a whole lot of throughput. Takeaway is limited, and so fundamentally, if you're in the Permian Basin, it's just really difficult to be able to cart away that natural gas, and it results in incentives that are just hard to solve. But there are other sources of emissions that I think are solvable with data. So for example, this is an open thief hatch. To solve this source of emissions, you simply shut the thief hatch. But it's an information problem because if you didn't know that it was open, you wouldn't have an indication. And just as a note for those who, again, apologies if this is too introductory, but this is a gas that's volatile, which means at standard atmospheric temperature and pressure, it might boil off. This, for example, is a formerly stuck dump valve that I found on a site. You can tell it's pretty small and it's easy to catch, but you just need to know what's going on. I think the first time I went out to the field and really started asking operators, hey, what is repair? What is the like repair part of leak detection or repair mean? I was kind of surprised at how skilled they were at fixing a lot of these emission sources. So this was a 3-step process from one of my favorite field techs at XTO, who said his process was first he kicks it with his boot. That doesn't work. He takes out a wrench and he hits it. And if that doesn't work, he takes out his water bottle cap because hydration is really important. And he just puts a little bit on some of the salted up parts. Of course, that doesn't fix everything. Sometimes you still have to order in a new part. But just to say, I think some of this is sorry, just laughing at Max. So some of these problems are easy to solve, but in order to reduce the emissions, that means we first need to find them. And I think that's kind of the paradigm we take to this at Project Canary, and where I really try and plug in. So when I was looking at what was needed in this space, I think traditionally what I saw was that there were a lot of super high accuracy sensors that, as a graduate student, I couldn't afford, didn't have access to, that needed a lot of expertise to operate. And what that meant was that the operating those instruments only happened periodically. And periodically, like, I want to be very clear, periodically is better than like never happens at all. But certainly, leave something to be desired. Additionally, like in the lower right, you see audiovisual olfactory inspections. They happen a lot more frequently, but miss a lot of potential emission sources. And one of the issues that we're running into now, or we have run into over the last 2020 with economic conditions, is that we've talked with operators who are really looking to cut costs and reduce some of those site visits. So, okay. What we're seeing here is what I saw the sensor landscape in terms of what was available for chemical detection on the market. So on the x-axis, pardon me, is accuracy or lower detection limit, and on the y-axis is cost. And we'd seen a lot of movement in the quote-unquote low-cost sensor space, particularly for measuring chemical constituents like CO2, NO2. In the upper right-hand corner, we have a lot of different high-end spectroscopic techniques. So think like your Picaros, your the Los Gatos analyzers that can really precisely measure one specific chemical constituent. But what we found was that this kind of middle ground was missing of a sensor that had a lower detection limit in the like hundreds of parts per billion and in the like thousands writ large. So that was really what Project Canary set out to solve. Now, I certainly again, I want to be a little bit careful here and be very respectful of the other approaches that are on this call to solve the problem of methane emissions. I think what I saw was that a lot of different approaches that would get the problem of like these emissions are everywhere by moving sensors around in novel ways. And I think, like, to be very clear, like if you are a plane, if you have a drone, if you have a satellite, like you are beating us on speed, right? Like I make no bones about that. Like continuous monitoring, it takes us like 20 minutes or so to set up one of our sensors, and then our field tech has to go to the next site. It's different than a plane. But what we are missing out on is that there is a trade-off fundamental. I mean, this is a fundamental problem in earth sciences, right? There's just a trade-off between how close you are to an emission source and how frequently you can get it. And so these are some estimated detection limits. I've got colleagues on the call who can tell me I'm like full of shit and wrong, and we can push back on this. But what I wanted to do is superimpose certain detection limits against some of Dave Allen's leak data that he took from one of his field studies. So in what you're seeing on the x-axis is leak size in grams per second. On the black or left y-axis is leak volume. On the right in blue is the cumulative leak fraction. And the takeaway here is that you can have different types of approaches that will get you great spatial coverage, but the detection limit in some of these more mobile approaches varies greatly. And I think one question I was asked a lot, particularly when I was fundraising for a company, was why can't satellites solve this? And what I typically tell folks is that the resolution of satellites is awesome for basin-wide inventories, but it can be difficult for operations. So really what we see is that continuous monitoring can really go hand in hand with some of the basin level detection methods. So this is an image from one of Daniel Cusworth's papers, looking at what would happen if we took the Avarice instrument and simply put that up on a satellite. It would no longer be a microsat, but if you used like best-in-class algorithms and threw a lot of money into launching this into space and could solve alignment, you would still get a lower resolution in both space and emission sources that I think would leave something to be desired. I think in terms of upcoming missions that are on the docket, there are certainly a lot of satellites in the space. We're really excited to see progress in this, and we're so happy to collaborate with the upcoming missions. But we don't think that the spatial resolution of this is something that's drastically going to change. I think the other dimension of this problem that's important is that many of these emission sources are intermittent. So this was just some random data I pulled from one of our dashboard, one of our sites, showing kind of what we see when we just look at the raw data, which is a lot of intermittency. And this, I think, and I know Dave Allen just published a paper on this that I unfortunately have yet to read, but I think really what this shows is that if you pick one specific point in time, then you may have depending on when you go, it's highly likely you could be missing many emission sources. Additionally, there are many types of sources that are both periodic but also growing over time. So this is some work that Aaron Tullis presented at AGU back in 2019 based off of data taken on one of my instruments back when pre-merger with Project Canary, where we concluded that by using high frequency monitoring, you could get faster emissions mitigation, you can get better insights into temporal patterns. So really, I think where I see Project Canary and my work slotting in is in this space of high accuracy or low detection limit, but high frequency of measurements that I think is going to be very, very important for operations of this instrument. I also think that this type of sensor fills in what has traditionally been a missing level of detection in a certain, what I think is the sweet spot. But I think the important thing to know is that when you place the sensor on site, it can capture most, if not nearly all, emissions, which I think is going to be important when we talk about, is this potentially a replacement for LDAR? And to add to why I think this is a good idea, these are some simulations run from FEAST, the Fugitive Emissions Abatement Simulation Toolkit, created by some very smart cookies, some of whom are here on the call, showing simulation of a direct detector or continuous monitor with about a 1 part per million precision compared to an automated infrared camera and a manual infrared camera. And what some of those simulations suggested is that you could actually get overall a higher net present value on those wells. This, of course, assumed pre-2019, I think, gas prices. Here are some maybe more updated results that look at overall emissions reductions compared to continuous monitoring or other types of leak detection and repair based surveys. The continuous monitoring program shown here in blue, and the results here would suggest that by using a continuous monitoring program coupled with an OGI camera, you can avoid overall upwards of 80% of emissions and more emissions than with simply using an OGI camera alone. So this is our CanaryX methane sensor as modeled by myself at Colorado State University's METEC facility. So this is a picture of our CanaryX methane sensor. This is a tunable laser diode absorption spectroscopy based approach coupled with a sonic anemometer. We do have the option in a couple weeks to be pairing this together with our traditional PID based measurement. It's all solar paneled, IoT enabled, sends the data up to our cloud. And the customers that we work with get access to the dashboard in real time. And I'll just step through this quickly. This is what that data looks like. This is, assuming this is May 6th, and I hit refresh before this talk, this is real-time data shown here in Methane. This is one of our customers who's allowed us to share some of this data, thanks to a partnership with the Colorado School of Mines, where we've actually got some students who've done some senior design thesis work on some data analysis projects on the site. So down here is the site map, where we see we've kind of doubled up on some of the sensors to allow some of the students to ask them research questions. Not all of our sites look like this, but this gives you a good idea of a traditional site in the DJ Basin. We couple this methane data together with the wind data to provide context to where the leak is coming from, and then issue alerts shown up here in this table based off of that. So operators can get issued an alert, they can click on this and go into the dashboard and pretty quickly identify a source and a duration for what that event is. We've recently added, although I can't figure out how to do it with this mouse, the ability to actually annotate these events to start tracking it, as well as real-time carbon accounting shown here. This is the flux coming off of that site in kilograms per hour of CH4, which is something that we can flip into a carbon accounting. Nice. And then on the bottom here is source probability for where those leak points were coming from. So not just an indicator of what the source is, but allowing the fact that there is some error and indeterminacy in this process. What we've seen this allow us to do is to catch issues and to catch them in the field fast, or faster than traditionally has been able to do. So for example, here are some, I think, typical issues that we've managed to catch and operators have managed to remediate in much quicker times than traditionally you would get with LDAR. Some of these are also not traditional, Quad OA LDAR sources, although I think, certainly some of the folks we have on the call here today do tend to go above and beyond regulations, but certainly not all producers do. I think of these different types of events that we've seen and caught and managed to get remediated, I think, unsurprisingly, open thief hatches is obviously a big one. Those we catch like super quick. If you have to send somebody back out to catch it, that's what causes the hours, not the minutes. And then my favorite example is the water hauler who ended up getting fired because they weren't connecting their vapor lines. They had been warned once or twice, and we worked together with the producer to put up a signage program and an education program to get folks to be using their vapor recovery lines. But the third time that we were able to catch it, we sent out an alert in 10 minutes, and that contractor was fired the next day and hasn't been working with that operator since. So just, again, I think this idea of continuous monitoring goes honestly beyond what we're doing at Project Canary, but these are just some lab evaluations that we've done. This is with an independent third-party lab that we had do these results, where we did a 5-point calibration looking at ranges from sort of 0 and 9 parts per million to 10,000 parts per million at STP, found an R² of about 0.99, which I thought was pretty good, a root mean squared error of about 87 over the entire dynamic range. And then more recently, we were testing these out in some pretty cold weather conditions at METEC. We ran several experiments, not all of which I have time to go through, but I was particularly excited about this one because we were able to see a leak of 0.1 grams per second as far away as 75 meters in a matter of minutes. And that actually exceeded the performance that I had been we had designed for and we had been promising to customers. We also are seeing good, well, we can argue over what good is, but I think we're also seeing reasonable agreement in terms of our own flux calculations with respect to the flow rates. I think this one, this idea of how can we do facility, essentially carbon accounting is where I think this is going in real time is really like the critical frontier here. I think that's what's going to enable really, this vision of a net zero world that I know is coming. And I think my personal biases can't get here soon enough. I think we're starting to see that the technology is allowing and enabling us to do that. So for the sake of facilitating maybe more of a discussion, I'm going to pause here and say, in conclusion, I think that continuous monitoring is critical to achieve the emissions reductions. I will just say on this other point, which I didn't talk about a whole lot, we are finding that market forces are driving the adoption of this emissions monitoring technology rather than regulators. I was just talking with a gas marketer this morning who was like, hey, I'm trying to find some gas for a certain buyer. It needs to come from the Permian, but I can't, they're not going to buy it if it's coming from a pad that has flaring. These are conversations that we're starting to have every day about what, I think the honest answer is like the bar is going up. And I think that, all of the it's going to take all of the technologies and it's going to take all of us to meet that need. But I think it's coming, and it's arriving faster than we would have initially thought. So with that, I'll leave it at that. And Evan, happy to take any questions.